The following is a progress report on our senior design project titled Spooled Tubing Unit. My name's Dino Beeler.
I'm Andre Aguilar.
I'm Kyle Brown.
And I'm Michael Navoy.
To start off, we're looking at an updated version of our timeline. What's marked off in green is what we have already accomplished to date. What's in yellow right here is what we are currently working on. We're trying to find a math teacher to guide us through our differential equations. And what's in red is what we plan on doing before the semester ends.
This is an overview of our meeting with Warren Hall. As a visual aid in our final presentation next semester, we intend to 3D print Figure 2, the helical pathway that our coiled tubing will take. To learn more about 3D printing, we met with Mr. Hall, the director of the Chevron Center for Engineering Education. During our meeting with Mr. Hall, we were able to attain the cost of the printing, which is $12 per cubic inch. Based on this price and the estimated size of our model, we are estimating the cost of our model to be within the range of $100 to $150. Mr. Hall also put us in contact with one of his student workers, Van Lee, an expert in 3D printing. Van Lee will be assisting us going forward from this point on with any questions we may have, as well as assisting us in adding the minute details to our SolidWorks design once we are closer to the completion of the project. We were also directed to use lynda.com, which includes many basic tutorials for using SolidWorks. One of the major constraints Van Lee is concerned about is our design not having internal supports, which would cause our model to collapse once printed. This will be one of our main focal points while constructing our model in SolidWorks.
In this slide, we're overviewing one of the first crucial moments in our senior design project, which was our meeting with Dr. Morthy. Our main goal in the first stage of our project is to correctly calculate the dimensions needed for the helical pattern in our spooled tubing unit design. To get an insight on how to begin calculating the helical pattern for our unit, we decided to meet with Dr. Suresh Morthy, who has a PhD in engineering mechanics. Because we have all endured the difficulty of his strengths and materials class, we figured he would give us the best guidance on how to begin our research. During the meeting, Dr. Morthy stressed the importance of learning the parametric curve equation and being able to apply it to our pattern. In our design plans, we want to run coiled tubing from a storage drum along a helical pathway to an injector head with an interior of a cone-shaped housing. Figure 1 shows a basic drawing of how our final helical pattern will look. As shown in Figure 1, Z is set as the axis of our cone. Dr. Morthy wants us to set up an equation which relates the x, y, and z coordinates as a function of S, which will help define the curvature of our helical pathway. The letter S will signal the length parameter along the helical pathway. Because our helical pattern will be inside of a cone-shaped housing, the radius of the cone at any length z would be the radius of a circle. Therefore, our starting cone equation would be x squared y squared equals linear z. X squared plus y squared equals radius squared, but keep in mind that the radius change along the length of the cone. Overall, Dr. Morthy wants us to take this parametric curve equation, research it, then find the curvature of the spiral in terms of the parameter S.
As instructed by Dr. Morthy, we began researching parametric equations for their relevance and application in our project. As defined by MathWorld, parametric equations are a set of expressions that express a set of quantities as explicit functions of a number of independent variables known as parameters. Following an online tutorial on Khan Academy, we were able to gain an understanding for curvature along a generic spherical helix. The parametric equations for this basic helix can be seen here to represent a circle along a vertical axis. The takeaway from this video is the fundamental steps for determining curvature. Finding the derivative of the parametric equations of the helix will give a tangent vector at a respective point on the helix. Relating this tangent vector function with respect to arc length will determine the curvature. Aside from the mathematical research, we acquired the technical manual for quality tubing products from the National Oil Well Barco website. This manual provides us with the physical limitations and specifications of coiled tubing for varying tubing diameters.
Having met with Dr. Morthy and researched what he instructed us to research, we began to attempt to apply what we learned to our specific project. Our design is actually a conical helix instead of a spherical helix. When incorporating a changing radius with respect to elevation in our parametric equations, it became apparent that we needed further guidance on the subject. I decided to reach out to my old differential equations professor, Dr. Guli Ding, for advice. Unfortunately, Dr. Ding was not knowledgeable on the topic. However, he did refer me to Dr. Mark Davidson, the author of the differential equations textbook we used in class. I've reached out to Dr. Davidson and we plan to work with him to find the appropriate curvatures that our coiled tubing will follow. Here you can see an example of some parametric equations used to produce a generic conical spiral. The h minus z over h term indicates changing radius with respect to height z, and here are some formulas for curvature and arc length of the conical helix in Figure 5.
As the industry advisor correspondent, I contacted our industry advisor, Mr. Stan Araby. I outlined our project goals and objectives and attached our literature review. After approving our project plans, he suggested we reconsider the spooling of the tubing. Currently, the helix pathway oscillates up and down through the use of hydraulics to store the tubing into the drum. After a discussion with the original designer, Mr. Johnny Van Way, he suggested we use a hydraulic drum and a stationary helix to reduce the amount of moving parts and simplify the process.